Hello everyone, welcome to Mastering Solutions. For this, let's start off by drawing a picture again to see how many phase shifts we have. It was kind of confusing to set this up just because of the wording of the problem. But what it is we have this protein, the reflectin with the 1.59, that is sandwiched in between the two other layers. I don't need that one down there. Okay, so down here, this is, we'll say R for the protein reflectin, and that's the N of 1.59. And it's surrounded on both sides by this other, what did they say? The cells with the index of 1.37. So we'll just say C for cells, 1.37, and C for cells of 1.37 index. So now when we draw the light coming through, we'll have from a low to a high. So we'll get a phase shift here, but now we're going from a high to a low, so we won't have a phase shift there. And then some of the light is reflected here. Some of the light's reflected, and like that. So we only have one phase shift, and they tell us in the question that we want constructive interference. So the equation that the diagrams in the book will give us with one phase shift for constructive interference is going to be 2t is equal to m plus 1/2 times lambda over n. Now, it's helpful to think about this because this right here comes from the relationship in the book where they said that the lambda of a material is equal to the lambda in air divided by the index of refraction. So this right here is where this is coming from to take into account the material. So whenever we solve for this, it's for that given material with the n. So now we need to isolate this for lambda. We want to find the longest wavelength of light in air that will give constructive interference. And so now what we can do is the m that we'll be using for this is going to be 0. So we'll have 2t is equal to 1/2 lambda over n. Now we can multiply both sides by n. So we'll have 2tn is equal to 1/2 lambda. And now we can multiply by the reciprocal, which is going to be 2 over 1, of course. So that will cancel that. And while we're multiplying this by 2, so lambda is equal to 4 times the thickness times the index of refraction. And because we're accounting for this here, this lambda is the lambda in air, which they're asking for in the question. We'll have, let's come up here and do it. Lambda is equal to 4 times the thickness. And they say the plates have a thickness of 62 nanometers. So 62 times 10 to the negative 9 meters times n, and that is going to be the n of the reflectin, so 1.59. So we have 4 times 62 nanometers times n, which is 1.59. So that gives us 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 394 nanometers is the longest wavelength that will give us constructive interference for this situation. And now before you go, I can hear some of you wondering, why did we use m equals 0 to get the longest wavelength? That seems backwards, right? And so let me briefly explain that. If we come back to our equation over here, where we have 2t equals m plus 1/2 times lambda over n, we're trying to isolate the lambda, right? So let's multiply this over. And so we'll have 2tn is equal to m plus 1/2 times lambda. And so to isolate this, we divide both sides by m plus 1/2. So that gives us lambda is equal to 2tn divided by m plus 1/2. Now you might see why now. The m is in the denominator. So the higher the m goes, the bigger the denominator is going to be. And just like any fraction, 1/2, 1/4, 1/8, whatever, the larger the denominator goes, the smaller the number is. So they wanted the longest possible wavelength for the constructive interference. So we want to use the smallest possible m, which in this case is going to be 0.